So in this video, we're going to review a little bit about integration by parts. So one of the most basic differentiation rules is the product rule. If we reverse the product rule, then we get the technique of integration by parts. So therefore, any check of an integration problem by integration by parts, will include the product rule for derivatives. Now, you should probably go back and see my notes from this topic on Calculus 1, Unit 5 on integration and anti-differentiation for a proof of the rule of integration by parts and for several introductory examples there. In this video, we're just going to kind of give a quick overview of that, work a few examples. So consider this a review or continuation of that earlier work. The basic rule is here. Integration by parts is the integral of u dv equals uv minus the integral of v du. So really it boils down to just a more complicated form of substitution. What we do is we take the integrand and differential product, the f of x times dx. F of x is we're integrating f of x dx. F of x is the integrand, dx is the differential. And we break that product into two parts. One is called u and the other is called dv. So we visualize the integral as the integral of u dv. Now the dx is always part of the dv, and then the f of x then can be possibly split up so that part of it is included in the dv and part is included in the u. Then from the u and the dv, we calculate the du and the v. We use the u to find du, which is by doing a derivative. Derivative of the u is the du. Technically, du is derivative of u with respect to x times dx, assuming x is your original variable. And we calculate the antiderivative of the dv to find v. So we're, the one part, the u part, we take a derivative to find du, and the dv part, we take an antiderivative to find v. Now at this point, you already have u, v, du, and dv, so then you just substitute into the second part here, the second side, the right side of the equation. You just multiply the u and the v, the u you started with and the v that we found, minus the integral of v du. And of course, notice that you still have an integral on the right side, but the hope is if things are working out right so that this technique will work, then this integral on the right is better to work with than the original one. So that's the basic idea. Integration by parts often works well when the integrand is the product of two different types of functions. So here's a table that shows you how to get started for the three categories, or for three categories where the integrand is described and where integration by parts is often useful. So before trying integration by parts, be sure that you first try to see if a basic substitution will work or not. And if it doesn't, then if it's the formula looks like what we've got here, then integration by parts often works. So if the integrand is a product of a polynomial and an exponential function, or it's the product of polynomial and a trig function, then that usually works pretty well. You let u be the polynomial. If it's just a linear function, you do integration by parts once, it all works out great. If the u, which is your polynomial, has higher degree, then you actually end up applying integration by parts multiple times, and we have a tabular method that works well. Another thing is if you have a logarithm function by itself, or the product of a logarithmic function and another kind of function. Sometimes then what will happen is we let u be the logarithm, and after you do integration by parts once, the logs will go away in one step. And if you have a product of an exponential and a trig function, particularly if it's a sine or cosine, then sometimes you can let u be the trig function, and you end up doing integration by parts twice, and it cycles back to where we started. So this is called a cyclic method. And I'll give you examples of at least one of each of these types. So if you've done this before, then I strongly suggest you just try to work these on your own before you see me work them. If you're doing it like I suggested, you will have studied my Unit 5 notes first, so this should be a review. So I'm going to ask you to pause after you see these and work them yourself. So here's one, the integral of x cosine of x dx. So see if you can work that one out yourself. Press pause now. All right, well here it is. Here's the details worked out. So notice that it is, there's no kind of basic substitution that's going to help us here. So we try integration by parts. We notice it is the product of two kinds of functions, an algebraic function and a trig function. So that's a case that integration by parts might work. Specifically, we have a polynomial function x and a trig function cosine of x. If you let the u be the x and then du is everything else, the cosine x dx, then this is going to work out for us. So notice that you have to have the dx as part of the dv. Now the u we're taking the derivative of to get du, so du is just 1 dx. And the derivative, antiderivative of cosine x is sine of x, and the dx goes away. So if we did the derivative of sine x, we get cosine x. Derivative of x, we get 1. All right, so that means the way we've got it, we have the integral of u dv. The x is the u, the cosine x dx is the dv, so this is equals, if we have this substitution. And by the integration by parts rule, this is equals uv minus integral of v to u. So you multiply these two together, u and v, so that's x sine x, minus the integral of multiply these two together, v du sine x dx. Well, see with the sine x is pretty easy, or cosine x would have been fine, but that x was kind of in the way, and the parts rule kind of allows us to get rid of that integration by parts. So anyway, this integral is easier to work. The integral or antiderivative of sine x is minus cosine x. That minus and that minus cancels, so it's x sine x plus cosine x. Our last integral sign is gone, so that's when we put our plus c. Here's a check using my GeoGebra app. X cosine x is the original function. I just set these at 0 so I won't see anything shaded for a definite integral. Of course, the definite integral says it's 0. That's irrelevant. But it comes up with an antiderivative right here, x sine x plus cosine x plus some constant. Right now that constant is 3. And so we see that it goes through the point 0, 4. When x is 0, sine of 0 is 0, x is 0, 0 times 0 is 0. Cosine of 0 is 1. 1 plus 3 is 4. So it goes through the point 0, 4 with the c being 3. Of course, choose a different c, and that's just going to give you a vertical shift. So you see graphed in blue here the original function, x cosine of x, and in green you see one specific antiderivative, and by moving this slider we could get all the different antiderivatives out of that. All right, here's another example for you to try. The integral of natural logarithm of x to the fifth times 6x squared minus 7 dx. See if you can do this one yourself. Come back when you've finished and check your answer against the work that's here. Press pause now. Well, this was the type up above. I said what you want to do is let u be the logarithm of x. You might even notice that log x was not one of our basic functions that we knew how to do an antiderivative for. In fact, if the function is just log of x, then you want to do it by parts and let u be just natural log of x. So u is log of x, or another log of x to the fifth. Another way to write that is 5 times natural log of x. dv then is everything else, the 6x squared minus 7 dx. So we work here on the right just a minute. We've got u, so we want to find du. Log of x to the fifth is 1 over x to the fifth times the derivative of x to the fifth, which is 5x to the fourth. And then we have our dx. The x to the fourth, x to the fifth cancel, that's 5 over x. Or had we started by just using our property of logarithms that said we can pull this exponent out front as a coefficient, it would have been even easier. It's 5 times the derivative of log x. Derivative of log x is 1 over x. So once again, either way, we get 5 over x dx. Over here, it's a polynomial, not too hard to find an antiderivative. Power goes up 1, that's power 3. Divide by the new power, 6 divided by 3 is 2. The constant term picks up an x. Don't worry about plus c here at this point. So with that substitution right there of what u and dv are, this is the integral of u dv. According to integration by parts, that's uv minus the integral of v du. Now it's just a matter of memorizing that rule, and now we just substitute in. Here's the u and the v, natural log of x to the fifth times this polynomial 2x cubed minus 7x, minus the integral of v du, multiply these two. 2x cubed minus 7x times 5 over x dx. Okay, so I'm going to go ahead and rewrite this natural log of x to the fifth as 5 natural log of x. And I'm going to factor an x out of this to bring it out here, which brings that down to power 2 and just a constant term there. Here I'm going to pull the 5 out front. I'm going to distribute the 1 over x here and here, so the powers go down 1. So we're just finding the integral of 2x squared minus 7. That's not hard to find an antiderivative of that one. The power goes up 1 to 3, divided by the new power, that's 2/3. This picks up an x. We still have the minus 5 out here, plus c, because our last integral sign's gone. That's the correct answer at that point. Let's see if we can maybe clean it up a little bit. Looks like I didn't do anything on that particular step. So we will just take that step out. So let's see, where were we? We were right here. I distributed this and made it 10x cubed natural log of x, and then minus 35x natural log of x. Here I made this negative 10/3 x cubed plus 35x plus c. So you can leave it like that, or if we want to kind of go the other direction and try to factor some stuff, not really factor because of the plus c, but without the if the c were 0, it would be factored. So all of these have an x in them, and I want to factor out, they all have a 5, and I'll get rid of the denominator by factoring out the 1/3 as well. So I'm going to factor out a 5/3 x. So what I'm really doing is, to find what's left, I want to go ahead and distribute really distribute a 3/5 and a 1 over x. So the 5 cancels that down to a 2 times, let's see, times the 3, and then an x squared log x. Well, there's the 2, there's the 3 log x. And then we have this one here. So let's see if this works out. 3 times 5/3 is 5. X times 2x squared is 10x cubed times log x. That's terms right. 3 times 5/3 is 5 times x times negative 7 is negative 35x, and we times that log x. Okay, so that part's correct. And then this part over here, I could, when we factor out the 5/3 x, that power goes down to 2, that power goes away, and the 3 and the 5 cancel, leaving a 2, and here the 5 cancels, leaving a 7 times the 3 is 21. And so we might, that's one way to write it. Probably this next to last one is probably as good as anything there on this one. Anyway, we could check any of these once we actually got rid of the last integral sign. Any of these last 3 lines would be a correct answer. We should be able to check any of them by putting the final answer, whichever one it is. I used the last line in y1, put numerical derivative in y2, and put the original function right there in y3 in a TI-84, and the tables for y2 and y3 should match. Notice that first one is 0.4 zeros and a 2, which is approximately the same as 0. These agreed at many places. Here is another way to write it. Here, when you did it in GeoGebra, I entered my function in here in my little app, checked antiderivative, there it is, and here's a graph of the original function here and an antiderivative there. Okay. All right, here's the next one. X to the fifth times e to the 2x dx. Once again, see if you can work this on your own. Come back when you're finished. So in this one, we repeatedly apply integration by parts multiple times. Each time, we let u be the polynomial or power function part, and let dv be the exponential part each time. And each time we do this, the power function decreases 1 in power, eventually going down to a constant function, which has a derivative of 0, so eventually makes it down to 0. We're going to use the tabular method for this. This works really well for ones like this. So the tabular method, you start with your original part that you want to be u, which is x to the fifth, and the dv is either the 2x. I'm not going to write the dx's down each time, but of course dx is part of dv. Now coming down this column on the left, we're taking derivatives. Okay, so x to the fifth, the derivative is 5x to the fourth. Derivative of that is 20x cubed. Derivative of that is 60x squared. Derivative of that's 120x. Derivative of that's 120, and the derivative of that is 0. So eventually it gets down to a derivative of 0. And this will happen always when you have a polynomial like this. Of course, the bigger the degree, the longer it'll take to get down to 0. Okay, this one here, the e to the 2x, we want to take an antiderivative. But the antiderivative really doesn't get much worse or better, really. It just stays pretty much the same. E to the u, the derivative is e to the u. So the antiderivative of the e to the 2x is e to the 2x. However, we really need to do a substitution here to get this to work out. So we're doing the antiderivative of e to the 2x, call 2x, say w. Then dw is 2dx. Then we need to balance with the 1/2. So each time we take an antiderivative here, we still get e to the 2x, but we multiply by another 1/2. So the first time we get a half e to the 2x, then we get 1/4 e to the 2x, then an eighth e to the 2x, then the fraction of the front is 16th, a 32nd, a 64th, and so forth. Now what we do here is we have an alternating sign column, plus, minus, plus, minus, plus, minus. So think of these as either positive 1 or negative 1. If we start up here, then we're multiplying along the diagonal. Positive 1 times x to the fifth times 1/2 e to the 2x. That's basically the uv part of the product. So that gives us our first term, 1/2 x to the fifth e to the 2x right here. Then we multiply across here, but we do the minus. That's because of the minus integral of v du. So the minus comes in here. So we get so we got 1/4 times 5 times negative 1 is negative 5/4 for coefficient. And we have an x to the fourth and an e to the 2x. Then the next one's going to be plus. We get 20x cubed times 1/8 e to the 2x. 20 times 1/8 is 28. That reduces to 5/2. We'll cancel a 4 out of the top and bottom. And then we have an x cubed and an e to the 2x. The next one is negative 1 times 60x squared times 1/16 e to the 2x. Of course, we get an x squared e to the 2x there. What about the coefficient? Well, we get a negative, positive, positive. That's going to multiply and give a negative. And we get 60/16. If we divide top and bottom by 4, that's 15/4. The next one is positive 120x times 1/32 e to the 2x. Again, we get an x and then an e to the 2x. And the coefficient is 120/32, which reduces, let's see, if you divide top and bottom by 8, that reduces to 15/4. And the next one is negative because of this sign here. Negative, positive, positive. So it's negative 120 times 1/64. That's 120/64. Divide top and bottom by 8, and you get negative 15/8, and it's e to the 2x. If we were to keep going, this is 0. This product would be 0, then another 0, and 0, 0, zeros forever. So this is the end of it. Of course, we just always have to have our plus c at the end. So that's the answer. It might be a little easier to write or cleaner if we notice that they all have an e to the 2x. And if you look at the denominators, they're all, the least common denominator of that least common multiple is 8. So I'm going to factor out a 1/8 and an e to the 2x. And what's left? So we're basically, the e to the 2x's are gone, and I'm distributing an 8. Half of 8 is 4 for that one. 8 divided by 4 is 2 times negative 5 is negative 10. 8 divided by 2 is 4 times 5 is 20. 8 divided by 4 is 2 times negative 15 is negative 30. 8 divided by 4 is 2 times positive 15 is positive 30. 8 divided by 8 is 1 times negative 15 is negative 15. So here we have this fifth degree polynomial, 4x to the fifth minus 10x to the fourth plus 20x cubed minus 30x squared plus 30x plus minus 15. And that's times 1/8 e to the 2x, and then we have a plus c at the end. So that we just did parts, I don't know, 5 or 6 times, a bunch of times there, and it worked out very nicely by having this tabular method to keep up with it. Okay, one more example. Let's see if you can do this one yourself. See if you can find the integral of e to the 2x sine of 3x. Okay, go ahead and press pause now. Okay, well, this is what we call the cyclic type. We're going to integrate by parts twice. And at the end of the second integration, we'll be kind of back to where we started. So let's just kind of do this a little at a time. You can actually let u or dv be either one. It's easier, I think, if you let u be the trig function, sine of 3x. And then dv is e to the 2x. We just talked about then the antiderivative of that is 1/2 e to the 2x. Basically, w is 2x, dw is 2dx, balanced with the 1/2. You get e to the w, and then you got the 1/2 out front. The derivative of sine of 3x is cosine of the 3x, so it's like another substitution. Let's say I've used u, v, and w. Call it z. Sine of z, the derivative is cosine of z times the derivative of z. Derivative of 3x is 3 dx. I got a dx. Okay, so with that substitution, this is u1 times dv1. It's the product of these two. And we know that according to parts, we get by multiplying u1 v1 and then minus the integral of v du. So we multiply these two together. That gives us 1/2 e to the x times sine of 3x minus the integral of multiplying these two together. 1/2 e to the 2x times 3 cosine of 3x dx. Let's see what we got here. I want to go ahead and get this minus inside here. And I'll get the 3 and the 1/2 and the minus together and make that negative 3/2. We still got a cosine of 3x and we still got an e to the 2x. And we got this term. So now we're going to do integration by parts again. And you want to do it kind of the same way. So the first one, we let u be the sine. So this time we're going to let u be the trig function. Negative 3/2 cosine of 3x. If you got any extra constants, I usually throw them in with the u part. Okay, the dv then is what's left, which is e to the 2x dx. Well, once again, that's the same as the v1 and v2 are the same. They're both 1/2 e to the 2x because dv1 and dv2 are the same. Okay. Okay, so the derivative here, derivative cosine of 3x, is sine of 3x with a minus sign. So that minus takes care of that minus, makes it a plus. And then we have to do the derivative inside, which is 3 times 3/2 is 9/2. And of course, it always picks up a dx there. All right, well, so this part right here is the integral of u2 dv2. So it's u2 v2 minus the integral of v2 du2. So that's just the integration by parts rule again. Okay, this part right here, first term comes down for the ride. u2 v2, that's multiplying these two. So negative 3/2 times 1/2 is negative 3/4. We have an e to the 2x and we have a cosine of 3x. Minus the integral, multiply these two together. So we have a 1/2 e to the 2x. And then we have a negative 3/2. No, this one, excuse me, down here. 9/2 sine of 3x dx. All right, well, when the dust settles, let's put these together. 9/2 times 1/2 is 9/4. Pull out up front, that's a negative 9/4. And we have this. And then you look at this for a minute and you say, oh my goodness, are we getting anywhere at all? Well, this thing right here is just like the beginning. In fact, it's exactly like the beginning, except over here the coefficient's 1. And over here the coefficient something is not 1. In this case, it's negative 9/4. Well, this is all equal to our original. So if I add 9/4 times this integral to both sides, this integral goes away. And here we're adding the same thing here with a different coefficient. We just add the coefficients, 1 plus 9/4. See, 1 is 4/4 plus 9/4 is 13/4. And that equals this. Now, technically, we should put a plus constant 1 here. Now, to solve for this integral, all we have to do is multiply both sides by 4/13. So there the answer is the answer. Let's just clean it up just slightly. From here, let's factor out a 1/4 and an e to the 2x out of this part. And so the 1/4 is going to cancel that 4, and the e to the 2x is there. So we have 1/13 e to the 2x. What's left? When we pull out a 1/4, we're basically multiplying this by 4. 4 times a half is 2. And we have a sine of 2x. Multiplying this by 4, the 4 cancels, so we get minus 3 cosine of 3x. The e to the 2x's are out front. And then we have a new constant, c. This new constant may be different than the old one for the same function, but it doesn't really matter. It's an arbitrary constant anyway. I guess this new c is 4/13 times the c1. But it doesn't really matter. We got an arbitrary constant at the end. We could check that with GeoGebra. E to the 2x times sine of 3x. It's telling us the antiderivative is e to the x times negative 3/13. That's what you get if you multiply this across. Times, let's see, cosine of 3x. Yeah, that's right. Plus 2/13 sine of 3x. They've got this in different order, but it's the same thing. 2/13 if I distribute it, sine of 3x. Yes. Plus the constant, of course. I'm showing it with the constant of 0 graphed. So the constant of 0 here. Let's look what happens when you plug in x is 0. 2 times 0 is 0. This is 1. 3 times 0 is 0. Sine of 0 is 0. This term is 0. 3 times 0 is 0. Cosine of 0 is 1. So this becomes negative 3. And this is 1. So it's negative 3/13. It's kind of hard to take. Negative 3/13 is kind of small. But this green graph here with this constant of 0 goes through 0, negative 3/13. So once again, be sure to see the complete set of notes, Calculus 1, Unit 5, Integration and Anti-Differentiation. I have a set of notes on that. And then I have a set of video lectures in my 5th playlist in this calculus section that go over that. Those notes go over these basic ideas more slowly. They develop it starting with some easier examples and then worked at some even harder ones than what you see here. It has 93 additional examples in all those videos and notes of the types of integrals that we've talked about here. The 15 integrations, or 16 I guess it is. I think that was 16. Yeah, the 16 integration there plus the 93, plus the 93 gives us 108 integration exercises altogether. And with those examples, you should be able to be in pretty good shape for getting these basic type of integrals going. So then I would suggest you study your textbook, whatever textbook you're using. Right now we're using Larson's book, and it's Chapter 8, Section 1 and 2. Section 1 is reviewing integration by substitution, and Section 2 is going integration by parts. And so with that, you can work all of homework set 1 as I have it set up as of this recording for my Calculus 2 class. So if you're in my Calculus 2 class, once you get to this point, you should be ready to get all of homework set 1.1 going. And we're going to go into some more advanced special techniques that I did not cover in the Unit 5 notes, starting with the next video in trigonometric integrals.